Now, in this system, this is a liquid level system. The deviation in flow rate to the first tank, so this tank here, is an impulse function of magnitude 5. Okay, so you have here the 5 Dirac delta of T. The following data apply. So you're given the areas of the 3 tanks. So tank 1 has 1 square feet and tanks 2 and 3 has 2 square feet for the area. So we don't have a through and through identical system. Now, our linear resistances are only for tanks 1 and 2 because the outflow on the third tank is constant. So it's regulated by this pump. So it's a constant. Now, in this problem, you are asked to determine the 3 expressions, the H1 of S, the H2 of S, the H3 of S. And we have H1, H2, and H3 are deviation in the tank levels for these same tanks. Now you are to sketch, so we will not do the sketching here to save us time. Although it says here that you're only going to sketch using the shape, or you will liken the shape to what we have in the responses for the different shapes of the curves for the impulse forcing function that was shown to you during the discussion. Then for letter C, you are to determine H1, H2, and H3. Now, it's suggested here that for H2 and H3, you are to use the graphs in chapter 7 of the text. So we will use the graph whenever time allows us, but we will all determine the things that we need to determine by the use of the formula, if a formula is available. Now, let me go to the board, okay? We'll just open the Jamboard for this. I will not anymore draw the system because it was shown to you already. So I'll go straight to the solution. We can go back to that particular part in the book where when we need some information. Just move this one. Okay. Wait, okay. So we go straight to the solution. For the first 2 tanks, based on the illustration, let me go back to the illustration. So the first 2 tanks in here are said to be non-interacting. And we have a ready-made formula for the transfer function of a non-interacting system for 2 tanks. So we can use that one, and then we will just connect it with the transfer function of this single tank. Now, as for this particular tank one, since we're also required for the H1 of S, then you already know how to determine its transfer function because that's our fundamental principle here applied to tanks connected in series. So we will try to do that in our board now. So if we'll write H1 of S, H1 of S over Q of S first, because that's where we're going to start to give the H1 of S. What do you think will be the transfer function of this system? Anybody? Based on our fundamental principle of the transfer function of a liquid level system. Can somebody give me the formula for this? The transfer function of a standalone liquid level system relating the level of the liquid in the tank to changes in the volumetric flow rate. Okay, somebody wrote in the chat box, so it's 1 over tau S plus 1. Okay, you have 1 over tau 1S plus 1. Okay, in this case, we will identify, thank you for that, Eugene. We will identify that tau 1S or specify it's tau 1S because we're talking of the first tank. Now, for tau 1S, we have the tau and its formula is A1 R1. So based on our given, your A1 is 1 and your R1 is 1. So meaning your tau 1 is 1. Okay, so we'll go back to the board. So this is 1 square feet and you have 1 for the resistance. So your tau is equal to 1. So for H1 of S over Q of S, we have 1 over S plus 1. Now, the problem is asking that we determine H1 of S, so then it is very important that we determine the H of S. Now, our H of S is the Laplace, or rather our Q of S is the Laplace of our Q of T. Now, our Q of T is a impulse forcing function of magnitude 5. So your Q of T then is 5 Dirac delta of T. And the transfer function of that, if we take the Laplace, would be simply 5. We know that because the Laplace of a unit impulse forcing function is the magnitude of that particular impulse function itself, which is 1. So it's the only function that does not have the S in its transform, in its Laplace transform. So in this case, that would be 5. So we have H1 of S equal now to, if this is 5, then I could transfer the 5 in here over S plus 1. So this is the first answer to the required information that we supply H1 of S. Okay. Now for H2 of S, go to the next page, we'll use the ready-made formula for the transfer function of a non-interacting system. So what would that be? The transfer function of two non-interacting system. So we have, you may use your phones. I think majority of you are not using your phones because you're writing on the chat box. Who has their phones on? That way we can have this answered right away. So what is H2 of S for a non-interacting tank in series? We're talking about two tanks. Anyone? Okay, we have one on the chat box. R2 over tau 1S plus 1 tau 2S plus 1. Correct. So that's our transfer function. Thank you, Antoinette, for our non-interacting tank in series. So we'll have it, sorry, sure, you share. Where's the Jamboard? So we have, actually it's 1 over tau 1S plus 1 times R2 over tau 2S plus 1. So we already have tau 1, so we now can go to determining the tau 2. And that's A2, R2. Now, as for the given in tank 2, so you have R2 as 1.5 and A2 as 2. So 2 and 1.5. Go back to our board. So you have here 2 and you have here 1.5. So this gives us a 3. Now you have H2 of S. Now we can place here 5 equal to 1 over S plus 1 times your R2, which is 1.5 over 3S plus 1. If we will convert this into something that looks like this so that later on it's easier, then we'll have H2 of S over 5 is equal to 1 over S plus 1. And we divide the denominator here and the numerator by 3. So that will give us a 0.5 over S plus 0.33. So that makes the coefficient of this S here equal to 1. Now, if we cross multiply the 5, your H2 of S then would be equal to 2.5, 5 times 0.5, and we have here S plus 1 multiplied to S plus 0.33. Now, this is the transfer function for this is the H2 of S that is being required for the system that is given. So the last one, we need the transfer function of the tank. This tank here, just go back to that particular problem. We need the transfer function of this tank. Now, we have discussed in the past what is the corresponding transfer function of a liquid level system in which the volumetric outflow is a constant in the case wherein you are provided with a tank, with a pump. In this case, you have a pump. So your volumetric outflow is a constant. We can still remember that one. And we will just simply make use of that. That way, we can get the overall transfer function of the 3-tank system. We can still remember. If not, we can go back to our, okay, so we have here the green box. It's 1 over AS. Okay, thank you for that, Sok. So your transfer function for the 3rd tank is 1 over AS. Now, let's see in this case, if you're really going to go back to the, shall we say, the model, the DE model for this 3rd tank, and check whether the ready-made transfer function that we had then for a single tank with a constant volumetric outflow will just work, okay, just for illustration purposes. So going back to the board, and we have it in here. If you're going to make a material balance, so if this is our 3rd tank, I'll just number it 3, and you have here, this is already Q2, and this is Q3. This is a constant. And you have, of course, the level here, which is H sub 3. Now, if you're going to write down the model DE for this, anyone who can still remember the model DE for this one, for the liquid level system, A DH3 TT is equal to, what's it's going in, minus Q3. Right? This is our model DE for this liquid level system. Now, at steady state, this is just to check whether what is provided to us or the ready-made transfer function for a liquid level system with constant volumetric outflow will work for this. Okay? So at steady state, this is 0, and you will have here Q sub 2 of S, and you will have here still Q sub 3 because it's a pump, it's a constant. So whether you have this at a non-steady state condition or steady state condition, the amount that is dispensed by the pump is a constant. So you have here Q3 is equal to Q sub 3 of S since we have a pump. So constant na siya. So we get to cancel this one. And what we have is the capital H3. I'll just go straight to the capital because, you know, it could be converted to the capital. And then we have capital Q sub 2. Okay, if we take the Laplace transform of this, you have AS H3 of S equal to Q sub 2 of S. Okay. And we can express this Q sub 2 of S in terms of level in tank 2, right? So you can write this as H sub 2 of S over R2, and I will have A. By the way, this A should be 3, this should be 3, this should be 3. S H sub 3 of S. Now, we want the transfer function, remember, of this third tank that we can use together with the ready-made transfer function of the two tanks that are non-interacting. That way, we can get the H3 of S or H of 3 of S. So the way we should write it, it should be output over input. So this one should be in the numerator. So I will place H3 of S, then I'll place this in the denominator, H2 of S. Then what we'll have here is a 1 in here. Then I'll have here this A sub 3 and S goes here in the denominator. So I will have A3 R2, A3 R2, and then the S. Okay? So in this case now, the transfer function that SOC has given to us is actually correct because the transfer function that he has provided is in terms of volumetric flow rate in here in here in the denominator, not in terms of level. So what SOC gave us is correct because we in this case here we have already converted the Q sub 2 of S in here, which should be in the original form of the transfer function of a liquid level system with constant volumetric outflow into level. That way we can manipulate it together with this. Okay? So tsakto to siyang ginhatag ni SOC. Now we just converted the Q sub 2 of S. So in this case now, we will place in here the values. So I think our A3 is equal to A2 as read a while ago. Let me check. Okay. Our A3 is also 2. Okay, so that's it. So I remember it correctly. So we can substitute here A3 and R2. So in that case, your placing it here, the final form, H sub 2 of S, that would be equal to 1 over your A, which is 2, and your R2, which is 1.5. We had it a while ago to be 1.5. Okay, in here. And we have S. So that then, this expression then, or I place it here, then would be equal to 1 over 3S. This is the one that we will use together with this transfer function that we have in here to get H3 of S. Okay, we'll just have this. Okay, so we have H3 of S over H2 of S times H2 of S multiplied to H2 of S, giving us H3 of S. So I'll now check what is this H3 over H2 in here. So we have 1 over 3S. So 1 over 3S, and it has to be multiplied to the expression that we had a while ago. So that expression of H2 of S is this, 2.5, and I have here a 1 and a 0.33 for the constant. So I do that in here. So I will have 2.5, S plus 1, and S plus 0.33. Okay, this is actually our H2 of S. This gives us the H3 of S. And as such, if you like to simplify further, the 2.5 divided by 3, you will have here in the denominator, then for H3 of S, okay, as it's rounded. So we can place here H3 of S equal to, so your denominator is S times S plus 1 times S plus 0.33. And we have 2.5 divided by 3. That would be 0.83 in here. Okay. So 0.83. And this is already our H3 of S. Okay, I think this is the first requirement in letter A. Now let me go back to the problem. So in here, you are to determine H1, H2, and H3 of S. Okay, letter B is sketching. We will not do that. And we will determine H1, H2, and H3 for the time 3.46. It was suggested here that we will get it on the graph. This time, we'll do it using the derived formula that are already available for us to use. Okay, so we will do that based on our H1S, H2S, and H3S expression. We will go back to our board. Okay. So we will get then our H1 of S. So we can, if you want to do the graphing class, you just go back to the graph of the liquid level system for an impulse response. Then for the time, you can read it out. So this is what I mean, just to give you an idea on how you do it in the graph. Let me share to you the book. What we'll do here is we'll determine it using the formula. Okay, let's go back to the chapter which gives you the impulse response. Just to outline how you're going to go about it. Okay, si linya kwaon sa graph. So pwede man na siya actually makwa gyapon sa graph. Okay, wait. Physical example siya. So we go to forcing functions. Here it is, chapter 4. This is for the sinusoidal. The impulse. That one is for the sinusoidal. We want the impulse. Okay, so for the impulse response, this is how it's going to be graphed, class, using MATLAB. So the graphing, however, is X versus Y. So we want the graph that expresses it in time, unit impulse. So here it is, class. This is the graph of a unit impulse response of a first order system. Now, in your case, you have to divide our, shall I say, our response there, H1 of S by 5, because the graph that you will be using is for a unit impulse response. What I mean is, if I go back to our whiteboard, this is our H1S. This is our H1 of S. And since we have an impulse forcing function of magnitude 5, and that graph is just only for 1, you have to divide this by 5. That way it will be applicable to that one. Okay? So in that case, this will, your response here, H1 of S will be 1 over S plus 1 only. Now, your tau here though, which is 1, is still applicable in that case to that particular graph. So if we go back to the graph, this is your tau y of t. Okay? Your tau y of t, and this is your t over tau. So since your tau is only 1, so you have no problem because these are all 1 and this is also 1. So in terms of the response to our particular problem, if you're going to read it from this graph, that time is 3.46. So you have 1, 2, 3, and this is the fourth. So you just more or less go a little bit before the half here. So that would be 3.46 and go up. And this is already your y of t. In our case, that would be our h So shall I say h1 of t? And since our magnitude is 5, then whatever is your readout here, since it's a unit impulse forcing function, you just multiply it to 5 because our magnitude there is 5. So it's just like at the initial, we just vision our h1 of s having no magnitude, it's just 1. But then once after you already get the y of t in here, you're just going to multiply it by 5. So I hope you get that one right. So the tau is 1. The time is 3.46. You go up with the y of t in here and multiply it by 5. That would be then your h1 of t read out from this particular graph. But if you're going to do it analytically, because that's how we usually do it, then you just have to invert, because anyway, that's so easy. This one is so easy to invert. So you have h1 of t being equal to 5 e raised to negative t. And that would be 5 e raised to negative 3.46 as required by the problem. So you will have an analytical answer here. That would really be very comparable to the one that you're going to read out from that particular graph. So in that sense, okay, that would be this answer. The answer here is 0.157. You can read this out also. You can read your answer. You can take your answer from that particular graph that I have shown, multiply it to 5, and you will still be getting h1 of t. Okay? Now, if we go to h2 of t, so that's where our higher order system will be applied already. Now, remember that if you want to do this analytically, if you go back to this one, where is that? Okay, you have this, okay? This is your H2 of S, and your denominator has to be in quadratic form, right? So we will do that. Remember, you have here an S plus 1 and an S plus 0.33. So I will place first here H2 of S. Your numerator, if it serves me right, is 2.5 S plus 1 and S plus 0.33. We want this to look like an expanded quadratic denominator. So what do we have in here? You have S squared plus 1.33 plus 0.33. There should be an S here. So 1.33 in the middle and a 0.33 here. And we have here a 2.5. Now, it is also very important that when you have the H2 of S expression, the form should be, as explained to you, this should be tau squared S squared in form. This should be 2 zeta tau S, and this should be 1. So if you recall, it was suggested that you divide the numerator by the constant that appears here on the last to make it 1. You do the same for your the denominator rather, and you do the same for the numerator. Now in this case, you will have now 1 divided by 0.33, so that would be 3.03 S squared. And your 1.33 will divide by 0.33. That would be 4.03 S. And you will have here now 1. Your numerator, you have here 0.825. Okay, so this is actually our transfer function. Actually, this is not the transfer function because we already multiplied it. If you recall, we already multiplied it with 5, which is our Q sub 2 of S. So if it's the transfer function that we want, the original that is, so ibutang to siya balik sa iyang original nga form. Since this was already multiplied by 5, we will divide it by 5. So this would be now 0.167. The denominator is still the same. Nothing happens to it. That way, our transfer function now will be really the same as that of a second order system. Now, okay, second order system in which the denominator is expanded and in quadratic form. Now, before I proceed, do you have any questions so far? When we determine the zeta here, by the way, when you determine the zeta here and the tau for our second order system, that way you can choose the appropriate response equation. It should be based on the transfer function. And since we already multiplied it with the Laplace transform of our forcing function, then we need to let it go back to the original. So, amo na nga nag-divide kita sa 5 kay ini, naka-multiply na ini sa 5 kay ina. Okay, so amo niya ang aton na transfer function. Now, with this now, your next goal, wala man question, is to determine the tau and the zeta. So, based on what we have there, by comparison, your tau squared, okay, may question. This excuse, ang numerator is 7.575 guro. Wait ha, where na siya iha naghalin? Hindi na siya naghalin. Eugene. Diin siya Eugene na anak. Lang ha.
Hello, miss. Sa 2.5 bilang miss ako, 2.5 divide 0.33 ko miss. Kaya ang 0.8 naka-multiply, miss.
Dahil lang iha. Check ko ha. This is 2.5. Yes.
Oh, miss, 2.5 divided by 0.33, miss.
Oo.
Ang 0.825, miss, naka-multiply na sa miss.
Multiply ni, sorry. 2.5 divided by 0.33. I thank you, Eugene. So this is 7.57. Sige. Kani, nagamay pa gid siya. Thank you. So you have here 7.57. So if we divide by 5, we have 1.515. Okay, thank you for that. So this is our then original transfer function. Please recheck my values, ha? You have this one now. So we're ready to get the tau and the zeta. So our tau squared in this case is 3.03. And your 2 zeta tau is 4.03. Okay? So if we get our tau, then our 3.03. You have 1.74 here. 1, you need to include that one. And then for this one, if you multiply it by our tau, if you multiply it by 2 and use it as the divisor for 4.03, your zeta would be so your zeta would be 1.158. Okay, kindly check my values. The very important value that we will be needing here is the zeta to choose the correct response equation. The ready-made response equation in this case. Is this correct? So you have 4.03 divided by 2 divided by 1.741. That would be 1.157. Sige. Now, this one then, based on the zeta value, is overdamped. And you are to choose response case 3 for the impulse forcing function. So allow me to go back to the PowerPoint and show to you the formula for that particular response. So for the impulse forcing function, if zeta is greater than 3, this will be your response equation. Okay? Where's my cell phone? So we will use this particular equation in determining our H2 of T then. So we'll just take a picture that way it will be easier to substitute later. Okay, so we will use this one. So we're going back to the Jamboard. And we will use the y of t response equation that we have there. This response equation, by the way, class, is for a unit impulse forcing function. So there's a need for us to multiply it with 5 later. So let me just give it to you here. So you have 1 over tau, 1 over square root of zeta squared minus 1 e raised to negative zeta t over tau hyperbolic sign of the square root of zeta squared minus t over tau. Let me just check if correct. It's t over tau. So this is our formula. If you're opening also the soft copy of the book, please check because at times I may have missed something in copying the formula in the slide. So 1 over tau times 1 over the square root of zeta squared minus 1 e raised to negative zeta over tau t hyperbolic sign of zeta squared. Oh, so say I missed something. Zeta squared. So this should be zeta squared minus 1. So it should be minus 1. And the t over tau should be not included in the radical sign. So t over tau. Okay? Now, we substitute our values. So in this case, 1 over 1.741 for tau. Then you have 1 over the square root of 1.1.57 squared minus 1 then we have the exponential function here, negative 1.157 over the tau, which is 1.741. And then we substitute the time, which is 3.46. Now, this exponential function will be further multiplied to the hyperbolic sign of your zeta 1.157 squared minus 1. This is its argument to be multiplied to t, which is 3.46 divided by tau, which is 1.741. So you will have your corresponding response here for this impulse forcing function. Our response here should be multiplied by 5. Since the response equation that is provided in the book is just for the unit impulse forcing function. Okay. Can you please solve and we'll check whether our values will be the same. Okay, I'll check class in the book whether this t over tau is the part of the argument of the hyperbolic sign because there's a difference if we'll process first the hyperbolic sign of the square root and then multiply it to t over tau. To be sure, wait. Kindly check it also from your end if That is the case. It's chapter 7. Okay, we have this. Okay, okay. Impulse. I'll just take a look at that. So it is hyperbolic sign of this multiplied to t over tau. What's your understanding of this class? I'd just like to ask, is your t over tau, okay, we'll make it bigger. Is your t over tau part of the argument of the hyperbolic sign, or it is separate? It has to be like 1 over tau, like this and this and this. What is your understanding of this? Because it would really matter in your final answer. If you're understanding, if it's not part of the hyperbolic sign argument. What do you think it is? Let me check from your end as students. How would you view it? Is this t over tau part of the argument of the hyperbolic sign, only separated from this radical expression, or not? Like we have this entire thing. Be? Part guro for me, miss. Sige, be. What about the others? Part guro for me. Sige, sige. Part of the hyperbolic siguro, miss. Ayan na. So, buong ko lang ni Balaklas na notice because this is the first time that I solve this problem to my students before I don't solve this one. Part. What about the rest? Kay wala t variable ang hyperbolic sign. I was just wondering why from my end I was also thinking hindi siya part. Nga part siya dapat, hindi siya pag-i-view nga hindi part kay amo niho. Actually, sakto ka mo, it has to be part of the hyperbolic function. Hindi gid siya pag-i-view nga hindi siya part sa hyperbolic function class. Kay kung amo na tani, ini ba lang tau, kung hindi siya part sa hyperbolic function nga ini, tani ginupod din na diho. Di kay nga awaya ginupod, so meaning part siya sang argument sang hyperbolic function nga ini. And one reasoning also is ti ang aton hyperbolic sign hindi na siya time dependent kung hindi mo siya pag-i-view nga hindi siya part sang argument sang hyperbolic sign. Although it would have been better to lessen the confusion of the one who's going to use this formula nga tani ginbutangan ini siya pag-print sang sang what you call this? Parentheses or bracket to ensure that the interpretation of this expression is that t over tau is part of the argument of the hyperbolic sign. So hindi gid siya pag-i-view nga hindi siya part kay dapat upod na ni sila nga duwa kung hindi siya part say tani nag-ubra na di 1 over tau square. So then what is our answer? If it's part of the argument, so this one will be processed as a whole and part of the argument of the hyperbolic sign. What's your answer? Okay, can you give me your answer? Okay. At least we have somebody. Eugene gave it to be 0.709. It's not yet multiplied by 5. So I will assume that it's not yet multiplied by 5.
Hello, miss. Na-multiply ko na sa gali, miss.
Na-multiply na siya. Sige,
Ah.
sige. So I will get the 5 in here. So na-multiply na siya. What about the rest? So we'll stick to this one unless you have a different answer. So specifically, we're not looking for y of t. We're looking for h3 of t. So I just wrote it there, y of t, based on the formula that I copied. So this is your h3 of t. And specifically, this is your h3 of 3.46 as the problem requires. Wait, wait. H2 pa lang. Wala pa ta ka H3 gali. H2 pa lang ni. So as to H3, what do we do? H3 of T is this one. Where is our H3 of T? H3 of S is this one. Since this is not anymore class second degree, you really have to do method of partial fractions for this one. So I made it look like this. That way, later on, when you do inversion, all your answers, your terms will have a constant and exponential function since ang imo factors gin-linearize ko na nga daan. Kung naka-quadratic pa siya budlay, kaya ma-manipulate ka pa sina sang imo denominator nga ipang perfect square mo para magkahimo ka either cosine, sine, or hyperbolic sine, hyperbolic cosine. I hope you can understand me. Okay, kung wala ni siya na written in linear factors, if it's written in quadratic form, mag-invert ka later on using inversion of Laplace. There's a need for you to use completing the square. That way, you will arrive at a sine function or a hyperbolic sine function, whichever of the two is applicable. Same thing with a cosine or a hyperbolic cosine. So I'm always suggesting to my student that convert your quadratic denominator in a form of linear factors. It's equivalent linear factors. So ini siya, I'm sure you know how to invert this one. Tapos naman lang ni siya mathematics. Once you have already inverted it, then just substitute the time 3.46. Do you get it? Hindi ko na pag-issue, but kay anyway, kadamo na makamusang mga examples ng inversion by partial fractions, and I know you fully know how to do it. Amhula ni siya galing, hindi ka mag-stick sa amuni nga form sa ang denominator. Kay maayawan ikaw mag-completing the square just so that your response will have the sine and the cosine function. And by the way, class, it doesn't follow that, for example, ang response ng imo classmate, ang function niya hyperbolic sine or hyperbolic cosine. Daso ng imo ang imo nga response niya nga puro niya exponential, nga ang iya hyperbolic sine and hyperbolic cosine. That is primarily because we have learned in our calculus that our hyperbolic functions, whether sine, cosine, and even the hyperbolic tangent, can have an equivalent expression in terms of an exponential function. So they are synonymous. So in this case, class, this is already a given that since I have written here quadratic factors, if you did not write it in its equivalent, I have given here linear factors, it is already a given, class, that your inversion, if you stick to the original quadratic function, it would be a hyperbolic sine or a hyperbolic cosine. Kay t, hindi man kita makaproduce ang exponential function equivalent po ang aton nga response cosine kag sine. Kaya wala na sila yung equivalent. So, expected, if you stick with this particular expression during inversion, your answer will be either a hyperbolic sine or a hyperbolic cosine or a conjugate of the two, for it to be equal to the equivalent response for this, which is actually exponential in form. So just do the mathematics and you'll be just fine. You just substitute the time 3.46. That's how you do it analytically. Now, in terms of the graph, we don't have a graph for H3 of t. We only have a graph for H2 of S and H2 of T and H1 of T. But as for H3 of T, we don't have because the plotted curves are all only applicable for second order systems. Hindi siya pwede sa third order system. Okay? Now, I'll borrow maybe a minute of your time. This is short regarding I'll go to the PowerPoint so I can discuss the transportation log. This is just short. Anyway, it's being approximated man. We don't normally process by inversion. A y of s expression or a function of s expression na nga naka-intact pa sa e raised to negative s because that would be using the second property of Laplace wherein you will have now the occurrence of the unit step function. Now, the last topic in this slide is the transportation lag, and this phenomenon is often encountered in flow systems. So anything that is flowing inside pipes are experiencing what we call transportation lag. Now, the other terms used to refer to this are the dead time or the distance velocity lag. Now, if you liken it to this particular simple illustration taken also from your textbook, we are to assume that the volumetric flow rate in any cross-section of this pipe is constant, given as well that the area is constant. And we have this length of our pipe. Now, x of t and y of t in here are temperatures. So x of t, temperature of the entering fluid, and y of t, temperature of the leaving fluid. So we could see here that your y of t, the output here lags behind the input by the value of tau. And that tau value is actually your volume of fluid entering the tank divided by the volumetric flow rate. Or shall we say the volume at a particular differential volume divided by the volumetric flow rate. So since this is volume divided by the volumetric flow rate, the tau still has the time unit. So it's the time required for this volume element, let's say we refer to this volume element of fluid, to travel from this section to this section. So we have considered then the volume of this entire section. Okay, and divide it by the volumetric flow rate, that gives us the time for the fluid element here to reach this point. Okay, that's the tau time for the transportation lag. For this system class, the response is e raised to negative s tau. And rather, the transfer function is e raised to negative s tau. It's not the response yet because we have the output here and the input. This is class the first time, and this is the only time in which the transfer function of a system is exponential in nature and not rational. We are used to seeing a rational transfer function, naka-fraction ng itsura. Iniya hindi, exponential siya. And as such, there's a need for us, and it's being discussed as well in text, that this particular exponential form of the transfer function of a transportation lag be, shall I say, replaced by an approximate equivalent. That way, in the process of inversion later on, we will not have to resort to producing an expression of the response. In this case, let's say y of t, that will be expressed in terms of u of t. Okay, I'm sure I know you recall your mathematics, your advanced math, and probably some was not able to grasp it last midterm, that this is comparable to e raised to negative as. And you know for one that if you have an expression, an exponential expression with the s as the argument, once it is inverted, mga u na siyang iyagwa. So it would be u of t minus, in this case here, tau. We write it in our advanced math as as, so it's always written as u of t minus a. If it's written like this, it would be u of t minus tau. Because when inverted, the exponential function with the argument s will always yield a u. And if you recall again, di ba, kasamok, may u ikaw, dason, kinanlan mo pa na siya ang iyang u of t minus a isulat sa interval form. What I mean with interval form is you have, let's say, for example, y of t equal to 1 on the interval t greater than 1 but less than 2, something like that. So we've done that in midterm. So karikot gid kung amo na. Kay kung u na siya, i-convert mo pa siya sa interval form, and then if the problem asks for the response at a particular time, you will have to select on your intervals there that you have written in which particular time it falls. So ano siya, karikot, and sometimes that others who are not able to grasp that particular concept of determining the response based on the designated interval, they will have it wrong. So Kauhanor has selected 3 different approximations in this case for the transportation log. Okay, ginpangitaan niya ni siya replacement. Ang replacement niya subong is also rational in form. So mangita sang expression nga hindi na mag u of t minus something ang inversion, but still would yield similar to the expressions in which upon inversion we can simply when we do inversion rather, we can simply do method of partial fractions. Hindi na kamo mag-u of t. Now, before I go to the approximate equation, there's a note here that the transportation log parameter tau is simply the time needed for the particle of fluid to flow from the entrance of the pipe to the exit, which I have mentioned a while ago. So in here, if you're going to plot the input, amo na siya, the output is really similar, more or less, in terms of graph to the input, but it only lags. So this is your input. If it's box type, this is your output. Box type man siya gyapon. Naglag lang siya by tau. So there's another scenario here wherein hindi na siya box type, naka-curve na siya, pero ang imo output, amo man na iya shape, naglag lang siya by tau time. So just like if you're going to apply it to real processes, if there's something that happens 1 meter or a 100 meters before a particular pipeline, mabatsagan na iyang effect sang sina nga change sa 100 before a particular pipeline set, tau time pa. Hindi na siya automatic nga may natabo diri 100 meters sa isa ka pipe length nga set. Automatic mabatsagan na siya dayon dito sa punta, hindi pa. It will take tau time for that particular disturbance to be, shall I say, felt on the next set of pipeline. If it happened like 100 meters before that set of pipeline. So amo na siya ang concept ng transportation lag. So para hindi budlay, Kauhanor suggests that you may choose from any of these 3 approximations. So, pwede nyo islan, so si e raised to negative s tau using Taylor's approximation by this one. So, if you look very closely to this class, ano lang man ini siya, di bala amo na siya ang transfer functions ang liquid level system. So, dogin replace mo lang ang imong piping system nga ang iya transfer function amo ni e raised to negative s tau by a liquid level system. Pero hapos ni siya i-invert. Kaya kung i-invert mo ni e raised to negative t over tau malang ang imo nga answer. San sa ini nga may mga u of t minus tau ka pa nga i-think. So ma-convert ka pa sa interval form. If you want another approximation, you have the first order pa day. Ini siya. Rational man siya gyapon. By the way, class, whatever is the tau value here, let's say this is 2, this will also be 2. If you have this as 1, this will also be 1. Okay? If this tau here is 3, you replace the taus here by 3 and simplify this expression. So, we also have the second order. Amo na siya ang second order, yung approximation. Okay, so second order in the sense nga ang imo rational expression in S, ang degree both sa numerator kag second sang denominator second degree. Diriya sa first order, first degree. Diriya sa Taylor yan nami, amo gini siyang pinakanami kay amo ni siya ang simple lang. So kung mag-process ka na method of partial fractions, wa mo after inversion, exponential function lang. So whenever you see So what does this particular topic now tell you to do? Whenever you see a transportation lag added to, or there's a need for it to be added to, let's say for example, to your liquid level system, kay base ang isa mo katangke 100 meters away kaysa sa isa. So i-add mo gid na siya. It's like you will attach it in series to another. Like first tank transfer function times this transfer function, then second tank transfer function. Masiling katimis nga ami sa okay tiyang imo tangke in the adjacent isa 100 meters away tidugay pa na tuya mabatsagan sang second tank mo ang disturbance sa first kay tungod may system nga in between sa ila. Ano na siya ang system? Ang imo piping system which has this particular transfer function. Di para hindi ka magproblema nga karikot nga mag-invert ako kita may u of t, di replace mo lang siya sini my suggestion always to my student is replace it by the Taylor series. Then it's like you have a first tank, then your piping system is approximated to a second tank because this is a tank also. And then the next tank to that is also the third tank. So it's like you have 3 tanks arranged in series, but actually you don't have that. You only have 2 tanks with piping which is long in between. Okay? That is why in the industry, tank if you class, if you notice, ang mga tangke as much as possible adjacent kina sila kay they want to eliminate the effect of the transportation lag. They want to eliminate this because the farther the equipments are to each other, you will have to really consider this one. And then sometimes kung hindi gid ma-avoid due to problema sa layout, then i-approximate lang siya. So pili ka kung which one is the best approximation. But having said that, which is the best approximation, you have this as the, shall I say, the step response approximation to the transportation lag. Our true real response is amo ni siya class ang number 4. Kita niyo ni siya, ang daw line lang nan. Amo na siya ha, ang aton nga real response. Kung nagamit ka sang approximation nga Taylor series, ang imo response amo ni kita mo ning curve nga daw exponential. Actually hindi siya exponential pero sige lang daw exponential ang shape na amo na siya. Kung gin second order pa day mo, ang second order ari siya class so nanaog siya anay at time 0 to negative 1. So nagsaka siya and ultimately will also rest on this 1.0 ultimate response here. The second order, which is number 3, ari siya oscillatory. Oscillatory, kinanaog siya anay sa 1, so nagsaka naman siya and eventually rest on the ultimate response here. So, kung tanawon ta, ano bala ang pinakahapos kag comparable nga response to the real response based on the 3 approximations. Ining tatlo ni. You have this as 1, you have this as 2, and you have this 3. Ako kung ako mangkoton nyo, I'd rather go with this one, the Taylor series approximation. Kaya why siya yaga negative? Kag eventually, although may sluggish siya nga part, magsiling class na sluggish, daw dugay siya mag-reach sa ultimate nga 1.0, pero ma-reach siya managyapon. San sa sini nga negative siya, hindi niya nag-1 na sa dayon, pero nanaog siya. So, the best and the simplest approximation of the 3 is actually the Taylor series. However, class, you may wonder, nga amis ging create pa na ang first order kag second order pa di approximation kung ang pinakanami si 1. As we have said already, because this first order and second order pa di approximation is not as sluggish as 1. Taas ila curve, so meaning faster sila mag-reach sa ultimate response. Ari siya hinay-hinay. Pero in terms of the complexity and the challenge of having to process the overall transfer function of your system wherein you have to consider transportation lag, ang pinakasimple si Taylor series. It's the simplest. Kiti kung tanawon mo na mag-invert kaya hapos lang ni siya iupod sa iban man nga amo ni itsura. Sa this one and this one. So if you are given the choice to approximate, it's always suggested that you use the Taylor series. Pero kung may software man lang available na i-plug in mo man lang niyo, siya na lang ma-invert niya, then let it be. Kaya dasi gini sila mag-rate sa ultimate response comparar sini sa iya.